Let's jump into this explainer. We're breaking down modulus functions, absolute values, and how they totally transform graphs. Pierre-Simon Laplace, the famous mathematician, was fascinated by how numbers have both a specific position and absolute value. Think about biologists mapping real-world physical boundaries. They use tools to project ground space onto coordinate planes.
Or take Formula One. Drivers face intense mathematical boundaries, like incredibly strict fuel limits to stay in the race.
So, what's a modulus? It's simply the absolute value, a number's pure, positive distance from zero on an axis. Algebraically, this splits into two paths. Positive values stay positive. For negative ones, just multiply by -1. Let's track some coordinates for the function x plus 2. You can see exactly how this transformation builds up. To actually graph this, just draw your line, spot the negative sections, and reflect them straight across the axis. This visual flip creates a sharp V shape. The line literally looks like it's bouncing right off the x-axis. Solving these algebraically is super cool. You literally split the equation into two separate paths, positive and negative. Or you can just square both sides. This forces everything to be positive and totally skips those separate cases. Graphs give us awesome visuals, but you absolutely need algebra to calculate precise spots when coordinates aren't perfect integers. This whole concept scales right up to inequalities. We're no longer just hunting for single points, but entire regions. On a 1D number line, an open circle means excluded boundaries, while a solid circle means it's completely included. In 2D space, you draw the boundary, test a coordinate, and just shade out whatever area you don't want. We've mastered straight lines. But what do you think happens to these reflections if we introduce wild, wavy cubic curves?